In this lecture, I would like to talk about the mapping from S-plane to Z-plane when there is a sampling involved in the process. Okay, so we know that when moving from start, Laplace transform to Z transform, we use this mapping to map S to Z. Okay, as you can see, this is a mapping from complex plane to another complex plane. Okay, and M of S is equal to e to the power ts. It's an important mapping, and we use this mapping almost everywhere in this class. Okay, starting from mapping signals, systems, and trying to find transfer functions of digital systems in discrete domain, and these kind of processes always relies on this mapping. Also, it's important to note the fact that, okay, let's assume that we have a planned GP of S, okay, or any continuous time transfer function. And if we somehow want to compute discretized transfer function, okay, what we do is we technically find the Z transform of GP of S times G zero order hold S, okay, which is equal to 1 minus e to the power minus 1 Z transform of G plant of S divided by S. Okay, so it's important to note the fact that if Z of P is a pole of G plant of S, then it's mapping, no, not Z of P, sorry for that. If, let's change the color, S of P is a pole of the plant, then we know that ZP e to the power TSP is a pole of G of Z. Okay, so the pole of the continuous time transfer function and its mapping is a pole of the discrete transfer function. Okay, and we know that poles are plays critical importance in control systems. Of course, zeros are important, but in general, poles they dominate the behavior in terms of stability and transient performance. Okay, now let's analyze this mapping using some examples. And let's start mapping of real line in S-plane, and this is S-plane, to Z-plane. So what is real line? Real line is this. Okay, this is the real line. Okay, in this mapping, S is simply equal to sigma, and sigma is element of R. Okay, so let's analyze Z. Z is equal to e to the power Ts, which is equal to e to the power T sigma. And as you can see, Z is also element of R, but moreover, it's always positive. So it is an element of R plus. Okay, so it's important because we map this. Okay, so let's look at this. Okay, so our first finding is all this part is mapped to this part. Okay, so we technically squeeze all real line into positive real line. Okay, there is some sort of reduction in terms of the area covered in the system. Okay, so moreover, let's analyze this. Okay, so what happens if sigma is less than 0? We are in open left half plane. Okay, so Z is equal to e to the power sigma t. Okay, since sigma is negative, as you can see, Z magnitude is less than 1. Okay, because sigma is equal to, sigma is negative. Okay, when Z is equal to 0, not Z, okay, sorry, let's change it. Okay, this is this case. We know that when sigma is equal to 0, Z is equal to 1, exactly 1. And when sigma is greater than 0, magnitude of Z is greater than 1. Okay, so now we get more information and let's look at the result. Okay, so this is sigma less than 0. This is sigma greater than 0. And here we have a point where sigma is equal to 0. Okay, sigma less than 0, which is the open left half plane part, or in the left part, is mapped to this part, whereas the positive real axis is mapped to almost equal axis, mapped to the part where sigma is greater than 1 and it goes to infinity. Okay, so if we, for example, go in this direction in S plane, we go in this direction Z plane. Okay, similarly for the unstable part, if we go in this direction in S plane, we go in this direction S plane. So they are both going different directions. And this 0, the origin is mapped to Z is equal to 1 point on the discrete time axis. Okay, so what is sigma less than 0? This is the pole. If it's a pole, we know that it is stable, right? Here, if pole is the magnitude of the, or like the real part of the pole is greater than 0, we know that it is unstable. And if it's at the origin, we know that it is marginally stable. Okay, let's analyze this. Okay, here our magnitude, the magnitude of the pole, if this is the pole we are mapping from S to Z plane, is less than 1. Okay, let's say it is A. Okay, so if A is a pole, we know that in the time domain solution we will have A to the power k, and when A is less than 1, we know that it will go to 0, so it is a stable pole behavior. Okay, similarly, if A is greater than 1, okay, we know that it's already positive, d to A to the power k, it will accumulate and it will go to infinity if k is going to be infinity, so it is unstable. Okay, so when A is equal to 1, we have 1 to the power k. 1 to the power k is constant, it's just 1. Okay, it's not going to 0, so it's not stable, but it's not blowing up, so it is marginal stable. As you can see, when mapping from S plane to the Z plane using this mapping, we preserve the core behavior in terms of stability of the pole. But of course, we are also mapping zeros, which is more complicated than mapping the pole behavior. Okay, good. So let's analyze some different mapping. Now let's try to map imaginary axis in S plane to Z plane, which is more tricky, as you can see in the derivations. Okay, so S is equal to J omega. Okay, we know that omega is a real number. We have positive j omega axis, negative j omega axis. Okay, so this is like this. Okay, which is good. So what we need to do is z is equal to e to the power ts, which is equal to e to the power tj omega. That's good. Okay, so first thing that obvious is, since j is a complex number, e to the something j is what its magnitude is equal to 1, right? It's always 1. Good, so we know something. Okay, so magnitude is equal to 1. So our mapping will be on the unit circle. It's guaranteed. Okay, this is nice. So let's look about the phase. Phase of z is equal to simply t omega. That's also true. The phase of t omega. But we know that when we talk about phase, what we do is it's also equal to t omega plus 2pk, right? Again, if, for example, if t omega is 30 degrees, we know that 30 degrees plus 360 is also like equal to the phase of z. Is similar to 30 minus 360 is also phase here. Okay, so there's a repetition and circular argument here. So k is equal to z. Yes, in general. Okay, so let's go back and let's analyze this. Okay, so we know that, but it's also true that e to the power t omega j is equal to e to the power t omega j plus 2 pi k j. This is also true because since this is true, this is also true because it's the phase. This means that e to the power t omega j is equal to e to the power t omega plus 2 pi k, is it true? J. Okay, so we are going somewhere here. So let's go here. That's good. So we have a mapping, and mapping is similar when we go from one place to the other place. Okay, so let's stick to here. Okay, So mapping M omega j, okay, this is the mapping. We are just mapping j omega is equal to mapping of omega, okay, omega plus 2p k divided by t, because we have t here, okay, so t is a part, okay, times j. Okay, this means that it is equal to m omega plus, so what is 2p divided by t? T is the period, sampling period. So 2 pi over t is the sampling frequency of the system times k multiplied with j. Okay, so what is this? There is a like repetition in the j omega axis. Okay, so we start from here. Okay, so we go until, for example, let's say here. Okay, so let's say this is j omega s divided by 2, j minus j omega s divided by 2. Okay, so let's color this like this. Okay, that's good. So let's change the color. Okay, as you can see, because of this repetition, one interval of sampling frequency is equal to the other interval of sampling frequency. So if we look at this, so let's change the color again. So let's look at this part. And here this is equal to j, 3 omega is divided by 2. Okay, if you look at this mapping of this section is equal to the mapping of this section. Okay, let's analyze in detail. It is the story. Okay, so technically we map this section to the unit circle. 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 This is technically similar to the aliasing or sampling behavior that you learned in digital signal processing course. But here we are not only sampling signals, we are also sampling the systems by the discretization process. Okay, so it means that maybe different kind of systems, okay, especially if they have complex conjugate poles, may have similar or same discretized behavior in the digital domain, which is also possible, even if we don't want that, and we will some requirements on sampling time, which I will talk about later. But this is the basic idea. So when we are mapping real axis, this is a one-to-one and onto mapping. Okay, but here, this is not a one-to-one mapping. It's many-to-one mapping. It's onto because we are technically covering whole unit circle. But this is infinite dimension, this is finite dimension. It's one of the problems. But as you can see, this is a repetition. So if I start from this point, I start here. And if I go in this direction, I will do that. Okay, this is good. So I will hit this point. Okay. Then if I go here, I will finish a circle and I go like this. It is just a repeated circle on the unit circle. Okay, so let's move on and let's analyze something different. Okay, very good. Okay, so what we did is we covered real axis. Okay, this is good. And we covered mapping of the imaginary axis. Now let's look at the mapping of the whole open left-half plane. In other words, this plane. Okay, so why open left-half plane important for us is the region of all stable poles. If you have a pole that's outside of open left-half plane, it means that you are stable. So mapping of this is technically important. Okay, so let's do that. So technically we covered this indirectly, but let's remember it again, no problem. Okay, S is sigma plus j omega. Okay, that's good. Z is equal to e to power t s. It is equal to e to power t sigma. Okay, it's alpha. Sorry, it should be sigma. Let's change it. Sigma times e to power t omega j. Okay, so magnitude of z is equal to e to power t sigma, where phase of z is equal to t omega plus 2 pi k. Okay, you know that k is an element of z. Okay, since we are mapping all open left half plane, okay, this is sigma. We know that sigma is less than 0, so magnitude is less than 1. Okay, so as you can see, this guarantees the stability. It's similar, right? Here, what's important is if you are in the open left-half plane or not. What defines being open left-half plane is the real part. Imaginary part doesn't have any effect on the absolute stability. Okay, and the phase, we have the same behavior. Okay, there's a repetition. This section, okay, has a similar effect, not similar, exact same effect with this section. This is exact same effect with this section. So if we look at the whole mapping, we obtain this behavior. Okay, as you can see, this is the result. So this is called primary strip. Okay, so all these strips are mapped to the unit circle. No, the region inside the unit circle, but not the unit circle is not covered. Okay, this blue is mapped to this blue. This purple part is also mapped to this blue. This is the secondary strip. This is the third strip. I don't know the name, but this basic idea is the whole important thing is there's a repetition with the strips. And this is the core main strip that we will try to stay inside is mapped to the unit circle. But also, let's say, if you have a pole here, mapping of this has the same effect of mapping of this. Okay, so it's not a unique mapping, especially in terms of the phase or complex part of the pole in the S-plane to the Z-plane. Okay, this is good. So what we want in control systems is, because omega S is the sampling time, is something that we design, okay, or we tune it. Okay, so if you have frequencies here in your plant, okay, the frequency components, it's general to increase your sampling time such that all of your poles stay inside the primary strip, such that you kind of know that at least your mapping is some sort of unique. It's not unique, but you know that this map is to this. But this is also mapped to that, but it's a very high frequency component, but it doesn't look like a high frequency component in the Z domain. So we try to stay here in terms of our design of the plant and digital control system. Okay, good. Now let's analyze this. Okay, so we know that this primary strip is mapped to the unit circle. Now let's analyze mapping of the path traced by the points 1, 2, 3, 4, and 5. Okay, it's kind of easy, right? But let's do that. Okay, so let's start with 1. Okay, 1 is S is equal to 0, e to the power ts. We know that. Okay, sorry for that. Okay, that's good. Z is equal to e to the power ts, is equal to 0, z is equal to 1. It's great. So we are at 1. 1 is here. 1, this is point 1, and we know that it is equal to 1. Okay, this is good. It's point 1. So we go from 1 to 2, but where? On the imaginary axis. No, not if we go on the imaginary axis S plane, we know that we will stay on the unit circle always. Okay, so what is 2? E to the power ts. Okay, so e to the power t times what is j omega s divided by 2. Okay, that's good. So what is omega s? Omega s is equal to 2 pi over 2. So this is equal to e to the power t, 2 pi divided by t, capital T times j. This is equal to, no, we have also 2, sorry for that, e to the power pi j. So phase is equal to pi. So we know that we will stay on the unit circle, and this is my 2. That's good. So we hit the 2. Now we keep the phase constant and move on the real axis. Okay, so in this line, we are not changing the phase, we are only changing the magnitude, right? So what's changing is z, which is equal to e to the power t sigma sigma is starting from 0. When it is 0, it's equal to 1. Sigma is going to minus infinity, so it's going to what? 0. 1 to 0. So magnitude is changing without the phase is changing. So we are going in this direction, and 3 is here. Okay, so we went in this direction. This is 3. Okay, so from 3 to 4, what's changing? It's technically not changing because so our magnitude is minus infinity. We are at the 0. Okay, our phase is changing, but we have infinitesimal small. But as you know, so in this direction, phases change from 0 to 2 pi. Here it will change from pi to 0, but in the other direction. So it will be like this. Okay. So this is 4. But this detail is not very important because 3 and 4 technically, theoretically, are at the same location. There's a change of phase, but magnitude is the same. Okay. From 4 to 5, we will go in negative infinity to 0 dimension. So e to the power t sigma is now going from 1, now going from 0 to 1. Okay, very good. So it is going in this direction. We are here. Now, finally, we need to finish this path, which is similar to this. It will do this. Okay, that's great. Okay, so the path from 3 to 4 is not important. This is the path. Okay, and since the primary strip is covering in this part, this also covers all this region. Okay, as you can see, sorry for that. This is the result. That's good. It's really good. Okay, now what is next? Okay, let's do something else. I think we covered the importance. These are more like examples. Okay, mapping of constant attenuation line. What is mapping of constant attenuation line? So we technically fix the position on the real axis and we move on the imaginary axis. We just changed it. Okay, we technically did this for geometric axis, but now we are changing the magnitude. So we know that phase will cover whole like from 0 to 2 pi, and we know that there are repetitions, but the important thing is what happens if we decrease magnitude towards negative direction, and what happens if we increase the magnitude in the positive direction. Okay, so important parts are simply this. Okay, so magnitude of z is equal to e to power t sigma. Okay, we know that phase is equal to phase of z is equal to t omega plus 2pk. Okay, so we know that the behavior is similar. When sigma is less than 0, what's that? We have a smaller circle because magnitude of z will be less than 1. When sigma is larger than 0, z will have a magnitude greater than 1, and the mapping will look like this. Okay, good. So this stable line will map to a circle inside the unit circle, which is smaller than the unit circle. Mapping of an unstable line is mapped to a circle also, but it is larger than the unit circle because it is unstable. And we all know that when we go from 0 to infinity, we technically cover the circle infinitely many times. Okay, so it's also one of the important facts. This is good. Okay, I really like this lecture because of nice figures and illustrations. Okay, that's good. So let's change it and solve more examples. Okay, let's change to object tracer. Okay, that's good. Okay, so mapping of maximum setting time region. Okay, so if you remember the setting time, okay, it can be like 4 seconds or 2 seconds is equal to 4, I think, divided by what? TS. No, 4 divided by sigma, where sigma is the real part of S, right? Okay, this was the idea. Okay, so if your pole is close to 0, your settling time is high. So you settle, you converge slower. So we want this to have a cap because we don't want our system to be slow. So what we want is, given a settling time value, we define a sigma threshold, let's say sigma threshold, okay? And we want our system to be in this region, right? Or we want our poles to be in this region. which will give a cap approximately, of course, give a cap on the setting time value. Okay, that's good. So we know that. So idea is where this mapping is mapped to the S-plane, which is easy. We already mapped that, which is simply a circle inside the unit circle. And we know that its magnitude is equal to, the radius is equal to e to the power sigma 1 t. Okay, we know that. And this region is technically what we are doing is we are covering the whole point left to this line. So we are covering all of the frequencies, but the magnitude of the pole is decreasing, or not magnitude, it's going to the negative axis. So it is staying strictly inside the unit circle, right? Not unit circle, the small circle here. Okay, and it's important in general what we want, that we want our poles to stay in a safe region where we have a stable but relatively good transient performance. Okay, that's good. So we have something else which is nice. I like it. Okay, mapping of constant frequency location. Okay, so we generally concentrate on lines vertically, but let's look at what happens if our frequency is constant like this. Okay, so let's assume that this is j omega, this is minus j omega. We know that if j omega is on the complex plane, minus j omega should be also complex plane because the conjugate pair assumption. Okay, that's good. Okay, so maximum less than times region, mapping else. Okay, so good. So what is z? Z is equal to e to the power sigma t e to the power omega tj. Okay, so magnitude of z is equal to e to the power sigma t. Phase omega t is equal to, okay, we know omega t. So here, as you can see, omega is constant, but sigma is changing. So the phase is constant. Okay, that's great. So phase is constant. What's changing is sigma. Sigma is changing here from minus infinity to infinity. So it covers the whole, since its magnitude, it's going from 0 to 1. So technically, magnitude-wise, we are covering all of the magnitude, but phase is constant. Okay, depending of the omega, your frequency can be like this, or it can be, let's say, like this. But it's important, right? So try to understand where omega is located. Okay, so let's look at these examples. So I have two different frequency candidates, omega 1 and omega 2. Okay, so omega 1 is less than half of the sampling frequency, okay, which is the Nyquist frequency. And if you are above Nyquist frequency, which is kind of useless because you map to different frequencies, but it is higher than the quarter of the sampling frequency. Whereas omega 2 is between 0 and quarter of the sampling frequency. Okay, so omega s divided by 4 is technically 90 degrees. Okay, so if I have a line here, so here, okay, I will be here. So in that respect, omega 2 should be, let's use red, like this. Okay, this is T omega 2, whereas omega 1 is higher than the quarter of sampling frequency. It should be somewhere here. Okay, this is T omega 2. It's the phase. Okay, let's check the result. As you can see, it's correct. Now let's solve examples, and these are typical examples you will encounter in the midterm. Okay, this. Okay, so what I want is I want to map this rectangular region into the z-plane. Okay, so what I will do is I will divide it into two. Okay, so what I will do is first, I will not ignore the frequencies. I will assume it like this. Okay, so I want to map this region. In the second phase, I will ignore the real parts, and I will try to map this region, and intersection will give us the final result. Let's start with the first one. Okay, this is good. So what I have is I have two lines on the real axis. Moreover, they are in the stable part. Okay, so I know that. So do you have? Okay, no problem. Okay, I know that I will stay strictly inside the unit circle. This is important. This is good. Okay, I will stay in the unit circle. Okay, so this is sigma 1. This is sigma 2. This has a smaller. This is technically closer to negative infinity. So it will have a smaller magnitude here. Okay. This will have a larger magnitude here. Okay. So I will cover region inside of this. Okay. So radiuses are important. So this is R2. This is R1. Okay. So where we compute R1 is the magnitude of Z here, which is equal to e to the power t, and t is equal to 1 second in this time. T times sigma. Sigma is what's minus 0.5. Okay, if I compute the results, this will be 0.6 approximately, and the small one will be 0.47. Okay, so it's a very thin torus, or so it's donut-like shape in the complex plane. Let's look at results. It should be correct. Yes, it's correct. Okay, good. So what we did is we covered the real part. Now let's ignore this, and let's assume that instead of that, I want to map this region, right? So what I have is I have a constant frequency line here. Okay, one is positive, one is negative, and I want to stay in between them. Okay, and it's also important fact that this is the real line. Okay, real line is covered inside this whole region. Okay, so what is the phase? It is 3 pi divided by 40. If I compute the frequency, I will technically obtain that the phase, constant phase, because it's equal to, in the composite, it's simply 3 pi divided by 4, right? Okay, that's good. It's 3 pi divided by, is it correct? Yes, it's 3 pi divided by 4. So what I will have is this. Okay, these are the upper limits. Okay, this is good. So, and I know that real line is covered, so technically I need to cover whole of this region. So it will look like an infinite dimensional Pac-Man. Okay, so this is going every direction. So it is an infinite dimensional Pac-Man. It's not finite dimension, it's infinite dimensional Pac-Man. Okay, so what I did is I found that first, okay, using one information. I found this using another information. I know that my region is intersection of these two. So if I intersect these two, I will obtain this final result.